The Estero Water Resources Center is owned and operated by the City of Santa Barbara and treats approximately 6 million gallons of municipal wastewater per day. Recently, the plant went through a major upgrade to the secondary treatment process. The purpose of this project was to improve the quality of the effluent water in order to make operation of the tertiary filters easier. The tertiary system was installed in 2015 and produces all the reclaimed water for the City of Santa Barbara to water golf courses, school lawns, landscape irrigation systems, and toilets along the waterfront. The wastewater treatment process can be thought of as removal of solids and nutrients from the influent water to the plant. Solids can include anything from organic material like food scraps to inorganic material like sand. The removal of solids creates two different trains, a liquid train and a solids train. The liquid train ultimately produces cleaned and disinfected effluent water that flows to the ocean and reclaimed water. The solids train ultimately produces biosolids that are composted and methane gas that is combusted to generate electricity that is used to power the plant. Two operations help to remove solids: physical separations and biological treatment. The physical separations slow down the water to allow enough time for heavy material to settle out. The biological treatment uses a community of microorganisms to consume carbon, nitrogen, and phosphorus-based compounds. The secondary project focused on upgrading the biological treatment in our liquid train to more completely remove nutrients and produce a significantly clearer effluent. The heart of the biological treatment centers on the aeration basins. These 6 170-foot-long tanks house the majority of the biomass in the system and are where the microorganisms, or bugs, do the magic of the treatment process. Bugs need food and oxygen to survive and replicate. Their food is provided by the nutrients in the influent water to the plant, and the process provides the oxygen through millions of tiny air bubbles passed through the basins. The bugs are kept in suspension in the aeration basins primarily by the mixing of the air bubbles. This suspension of water and microorganisms is called mixed liquor and is the dark brown-colored water seen here. The rich brown color indicates a healthy biomass. The crux of the secondary project was on increasing the concentration of microorganisms in the aeration basins. By increasing the concentration, the total biomass within the system increased, and as a result, the time that a single cell theoretically spends within the system also increases. This time is called the Solids Retention Time, or SRT, and is the main measurement that operators use to guide operational decisions. The SRT is typically measured in days and indicates the level and type of treatment achieved in the aeration basins. Prior to this project, the plant operated at an SRT around 2.3 days. Now the plant operates at an SRT of around 9 days. This increase of SRT means that the basins house a very different, much older, and more robust set of microorganisms. At the old 2.3-day SRT, the bugs mainly fed on carbon-based food. Now, with the longer SRT, the bugs feed on carbon, nitrogen, and phosphorus-based food. This wider consumption of food equates to more nutrients being removed from the water, and ultimately a cleaner effluent stream. The workhorses providing air for all the bubbles are 800 horsepower single-stage turbo blowers. As part of the secondary project, 2 new blowers replaced our aging existing blowers. Even with the new and more efficient technology, the blowers still constitute the majority of electrical demand at Estero. Also included in this project were 5,800 new 9-inch fine air diffusers. These new diffusers produce much smaller bubbles than the old diffusers. The result is a significant increase of air-water surface area, which means a more efficient transfer of oxygen to the water. In contrast to the aerated zones, there are also a new anaerobic and anoxic zone within each basin. These new zones, paired with parabolic mixers, are important to the nitrification and denitrification process. Specifically in the anoxic zone, the bugs break up nitrate and release nitrogen gas to the atmosphere. The resulting drop in nitrogen concentration within the liquid stream produces a significantly cleaner effluent than strictly carbon-based treatment. Other additions as part of the secondary project were cutthroat flumes at the entry to each aeration basin. In order to feed each aeration basin equally, these flumes regulate the flow to spread evenly between all basins. There are 2 flumes per basin, one at the head of the basin and one at the midpoint. The bugs within the aeration basins use the nutrients to do a few things: create energy and synthesize, or create new bugs. If left unattended, the bugs would continuously replicate and increase their numbers within the basins. To mitigate their growth and maintain a desired concentration, operators waste a certain mass of microorganisms daily that approximately equals the growth rate of the bugs. Wasting the biomass means sending it to the solids train, where it is further processed and ultimately turned to methane gas and biosolids. After leaving each reactor, the mixed liquor enters a common channel that combines flow from all 6 reactors. This common channel feeds the wasting gate, which is an automated V-shaped gate that allows mixed liquor to enter the solids train at a precise rate determined by the operators. Downstream of this wasting gate, a flume distribution structure was installed. This structure contains 7 flumes that feed 7 different secondary clarifiers. From the flume structure, the water enters one of the 7 secondary clarifiers. The purpose of the clarifiers is to slow the water down and allow it time to settle out the suspended microorganisms from the reactors. This settling has a few functions. It clears the water significantly before exiting the plant and allows us to reclaim our bugs that we worked to grow in the reactors. There are a series of scrapers that run slowly along the surface of the water and bottom of the tanks to collect the floating and sinking material. The floating material is called scum, and the sinking material is called sludge. The scum is sent to the solids train, and the sludge is returned to the head of the aeration basins to maintain the treatment process. Part of this project replaced the sludge pumps with newer equipment, added a new one, and increased the size of piping carrying the return sludge to allow greater flows. The clarified water flows over the weirs at the tail end of the clarifiers. From there, it goes up to 3 different directions: to the disinfection chamber, which adds sodium hypochlorite or bleach to kill any remaining pathogens before discharging to the ocean; to the tertiary system that produces reclaimed water; or to the secondary effluent return, or SER. The flow coming into the plant varies throughout the day as customers use water. The plant's peak flow time is between 9 and 10 a.m., when the flow from people waking up and completing their morning routine reaches the plant. The lowest flow occurs between 3 a.m. and 6 a.m. The diurnal nature of the flow creates a few issues for treatment as the water levels change. The SER system returns a portion of our clean secondary effluent to the head of the plant in order to keep the flow and levels constant. The operators set a total flow rate they want through the plant, and the SER returns the difference between the influent flow rate and the set point. This recycle flow is controlled by a hydraulic valve, which allows precise control over the flow of water. The SER has been important in freshening the head of the plant, preventing septic conditions, and decreasing wear on pumping equipment from frequent cycling on and off. The last section of the project was the new chemical addition station. The new bugs consume alkalinity in the water, think carbon dioxide, to oxidize ammonia. Sodium hydroxide, a strong base, is then added to the aeration basins to replace the alkalinity and control pH. As a result of the more complete treatment of the water, there now is significantly less ammonia in the effluent water. Ammonia plays an important role in final disinfection of the effluent. It reacts with the chlorine in the bleach to kill pathogens. To replace this ammonia for disinfection, we now add liquid ammonium sulfate just downstream of the SER valve. Both chemicals were novel additions to the plant. Since the system went online in February of 2019, treatment has improved substantially. One measure of water's quality is its turbidity, or clarity. Turbidity is measured in NTU. Previously, the effluent from Estero ranged between 8 and 10 NTU. Currently, our effluent is averaging 2 NTU, with periods in the morning near 1 NTU. For comparison, drinking water from Cater Water Treatment Plant is usually 0.03 NTU. Subsequently, the filterability of the water has increased substantially. The tertiary reclaimed water system works by pushing the clarified water through a series of straw-like filters with pores that are 0.01 microns in diameter, or ultrafiltration grade. If there are too many compounds in the water, these pores will become plugged and not allow water to pass through. This blockage requires operators to clean the system, and the frequency of these cleanings are indicative of the quality of the influent water to the system. Since the secondary project has been completed, the frequency of tertiary cleanings has decreased noticeably. Staff are excited for the many years of service this project will provide, and the improved water quality Estero produces as a result.